You are sitting in a familiar space. The objects around you, the walls, the furniture, the devices you touch every day appear stable, solid, and predictable. Time feels linear. Light traveled in straight lines. Cause leads to effect. You move, you observe, and you rely on the consistency of these assumptions. Yet, beneath this apparent normalcy, the universe quietly asserts truths that defy intuitive understanding. The cosmic microwave background, the residue of the universe's birth, is nearly uniform, but contains minute anomalies that should not exist. Dark energy, inferred from the accelerated expansion of the cosmos, dominates the universe in a way that no local experiment could ever reveal. Black holes warp space-time so radically that the very notion of a boundary between inside and outside becomes ambiguous. Nothing you are about to encounter is fiction. Every observation has been measured, every calculation verified. What is disturbing is not imagination, but inevitability. The universe behaves in ways your senses cannot grasp, in ways that challenge every expectation rooted in your immediate experience. This video will explore the 20 most terrifying theories that science has observed, calculated, or inferred, but does not widely discuss. Each represents a fracture in the structure of reality, a conflict between what is measured and what is comprehensible. You will be asked to confront contradictions that exist independently of belief or desire, and in doing so, you will see how fragile your assumptions about the world truly are. The vacuum that pushes you. Assume that empty space is inert. A vacuum is nothing, and nothing does not act. Yet the expansion of the universe tells a different story. Space is producing energy as it grows, accelerating galaxies apart without any apparent cause. The void is not passive. It exerts pressure, reshaping distances on a cosmic scale. The very fabric of nothingness possesses measurable influence over reality. When you look around your room, the space between objects seems irrelevant. The emptiness between the chair and the floor, the air that cushions your movements, these gaps appear as absences rather than presences. Yet, at the cosmological level, emptiness is neither neutral nor empty in any conventional sense. Observations of distant supernovae reveal that galaxies are receding faster over time, accelerating away from each other at rates that cannot be explained by the gravity of visible matter. The expansion is not slowing under mutual attraction. It is speeding up, an effect attributed to a property of space itself. Vacuum energy. Vacuum energy is predicted by quantum field theory. Even in a region devoid of matter or radiation, quantum mechanics dictates that particles and antiparticles constantly fluctuate into and out of existence. These zero-point fluctuations cannot be observed directly, yet their cumulative effect contributes a small, persistent pressure throughout the cosmos. This pressure acts oppositely to gravity, pushing matter apart. The very nothing you inhabit is imbued with a capacity to reshape the universe on the largest scales. The implications are profound and unsettling. If the vacuum can accelerate the expansion of the cosmos, then empty space is not simply a backdrop on which events unfold. It is a dynamic entity, actively participating in the evolution of reality. The emptiness between galaxies has energy. The absence around you has influence. Every cubic meter of space carries a latent force that, over billions of years, alters the trajectories of countless celestial bodies. What you perceive as nothingness is, in fact, a driver of motion and structure. Moreover, the density of this vacuum energy appears remarkably small, yet constant across vast regions of space. It is uniform, unchanging, and indifferent to the presence of matter. The accelerating universe is not chaotic or uneven. It is precise, governed by the quiet insistence of the Usta vacuum. Measurements using type Ia supernovae as standard candles show that this expansion began dominating the universe only relatively recently, after billions of years of gravitational deceleration. The force is subtle, cumulative, and inevitable. You might assume that energy requires matter, that pressure is the result of collisions, that force is expressed through interaction. The vacuum challenges every assumption. Its effect is absolute and pervasive. It is measured not through contact, but through the movement of galaxies, through shifts in the redshift of light traveling billions of light years. It cannot be contained, altered, or shielded against. Your instruments detect its consequence, and through those instruments, you witness the universe being pushed apart by what seems to be nothing. In a sense, the vacuum is a silent dictator. It enforces its will through the very framework of space-time, indifferent to every structure, every star, every planet, including the one beneath your feet. Nothing exerts influence without being noticed. And yet, the vacuum exerts influence precisely through its invisibility. Its action is unobservable directly, but it is inferred with certainty through the consistent expansion of the cosmos. The consequence of this is both precise and disquieting. The universe is not only expanding, but doing so under the influence of a force that is fundamentally intangible. an omnipresent pressure that arises from the absence of everything you consider real. Your intuition about space, about void, about emptiness is inadequate. The cosmos is not a passive stage for events. The stage itself moves, pushes, and shapes every act it contains. You are surrounded by nothing. And yet, that nothing is active, patient, and inexorable. It is the quietest engine of change, operating across incomprehensible distances, reshaping time and scale without recognition. The universe, in its expansion, is driven not by what exists, but by what does not. And in that realization, the stability you assume in your immediate reality begins to fracture dark matter's invisible architecture. Everything you see, the planets, the stars, the galaxies, comprises only a fraction of what exists. Observations of galactic rotation reveal a gravitational scaffolding that is undetectable by light. This unseen matter dictates motion, yet cannot be observed. The universe is dominated by a presence you cannot perceive, an architecture that structures everything while remaining fundamentally invisible. When you look at a spiral galaxy, the stars in its outer arms move faster than expected, defying the predictions of visible mass. According to Newtonian mechanics, these stars should slow. Some even escape the galaxy entirely. They do not. Their motion suggests the presence of mass you cannot see, mass that exerts gravitational influence without interacting with light, radiation, or ordinary matter. The galaxy's structure is held together by something intangible, something that only reveals itself through its effect on the objects you can observe. This invisible framework is what physicists call dark matter. It is not a hypothesis created for convenience. Its existence is demanded by consistent, repeated observations across galaxies, clusters, and the cosmic web. Gravitational lensing, the bending of light from distant galaxies, shows that regions of space contain far more mass than can be accounted for by stars, gamma, or dust. These measurements are precise, verifiable, and inescapable. Wherever ordinary matter is found, it is accompanied by an invisible counterpart, forming a hidden backbone that determines the shape and evolution of the cosmos. Dark matter is both omnipresent and elusive. It passes through your body without interaction. It does not emit, absorb, or scatter light. Its influence is gravitational only. Yet that influence dominates the dynamics of galaxies and clusters. You might assume that the universe is composed mostly of what you can detect, what you can see, touch, or measure directly. Observation contradicts that assumption. The majority of matter, the majority of mass, is fundamentally unobservable. Reality is composed less of what you perceive and more of a silent, invisible architecture that structures every cosmic formation. The implications of this are profound. Galaxies form, rotate, and cluster under the guidance of something you cannot detect. Large-scale simulations of the universe rely on dark matter to replicate the filamentary structure known as the cosmic web. Stars and galaxies do not scatter randomly through space. They trace the contours of an unseen lattice. You might imagine space as a simple void punctuated by luminous objects. Instead, it is a lattice of hidden influence, and the light you perceive is only the tip of a vast, gravitationally coherent skeleton. Furthermore, dark matter exists not just in galaxies, but throughout the universe. Its density is low, but it is distributed broadly and uniformly, forming a persistent background that permeates every region. You are immersed in it now. Every movement, every orbit, every interaction on cosmic scales is subtly shaped by a substance you cannot sense. Your measurements are incomplete. Your understanding of matter is partial. What you observe as solid and definite is in reality contingent upon something invisible, dictating motion and structure without ever revealing itself to your senses. Attempts to detect dark matter directly have so far failed. Experiments deep underground, shielded from cosmic radiation, have not yet captured a single particle. Theories abound: weakly interacting massive particles, axions, sterile neutrinos. But the universe offers no confirmation beyond the gravitational evidence that first indicated its presence. It is a substance defined by absence, absent in sight, absent in touch, yet omnipresent in effect. This hidden framework also implies fragility in our understanding. If the majority of mass is invisible, then your intuitive perception of cosmic balance is incomplete. Collisions, rotations, and stability occur in response to forces you cannot perceive. The cosmos behaves in ways that cannot be deduced from observation alone, requiring inference from subtle effects. And the inferences themselves suggest a universe structured around what is unseen. You inhabit a universe dominated by shadows. Light illuminates only a fraction of reality. The galaxies, stars, and planets you can see are arranged according to a silent blueprint, an invisible architecture that holds everything in place. Your understanding of structure, motion, and scale is provisional, contingent upon an omnipresent substance whose reality is confirmed only through the motion it imposes. The visible universe is merely decoration. The invisible is fundamental. Black holes as time. Distorters. You trust that time flows uniformly. A second passes for you as it does for brats, everyone. Approaching a black hole, this assumption collapses. Time slows relative to distant observers, stretching moments into near eternity. These regions are not anomalies, but extreme amplifications of space-time behavior, showing that time is not an absolute river, but a malleable dimension, reshaped by mass and gravity. Every object, including yourself, experiences time as a consistent progression, measured by the tick of a clock or the rhythm of a heartbeat. Yet the equations of general relativity predict, and observation confirms, that in regions of intense gravity, the rate at which time passes is not fixed. Near a black hole, the curvature of space-time becomes so extreme that temporal flow diverges from the experience of an observer far away. If you were to descend toward the event horizon, seconds for you could correspond to years, centuries, or even millennia for someone watching from a safe distance. Time itself fractures along the contours of gravity. The distortion is not a matter of perception. Astronomers have measured the effects of gravitational time dilation in more accessible contexts, using clocks in orbit around Earth. Clocks closer to the planet tick slightly slower than those farther away. Near a black hole, this effect becomes overwhelming. A star orbiting close to Sagittarius A, the supermassive black hole at the center of the Milky Way, experiences measurable discrepancies in timing relative to distant stars. These differences are predictable and precise, calculated from the mass of the black hole and the geometry of the surrounding space-time. As you approach the event horizon, the contrast grows. The black hole's gravity stretches space and time into a funnel that funnels your experience into an extreme divergence from the external universe. Signals you send outward appear increasingly red-shifted, stretched toward longer wavelengths. To a distant observer, your descent slows, asymptotically approaching a standstill at the horizon. From your perspective, however, time continues normally, and events in the external universe appear to accelerate, passing in fast motion. Two observers in the same vicinity experience the universe in fundamentally different ways. This phenomenon exposes the fragility of assumptions about simultaneity and causality. If time is malleable, then cause and effect are not universal constants, but local experiences. What you consider the future might already be long past elsewhere, or still unfolding, depending on your position in space-time. The reality you inhabit is relative, contingent on gravitational geometry rather than absolute measure. Furthermore, black holes exemplify the limits of observation. The event horizon marks a boundary beyond which information cannot escape to the outside. Any object crossing that boundary ceases to communicate with the external universe. To an outside observer, the object appears frozen in time, suspended in a distorted limbo. Its fate is mathematically determined, yet physically inaccessible. Information about the interior is hidden, not destroyed, leaving the laws of physics intact but unobservable. Time has fractured into accessible and inaccessible domains, separating the known from the unknowable. Even the concept of now loses its universality. Near a black hole, every tick of a clock is contextual, dependent on proximity to mass, velocity, and gravitational curvature. The uniformity of time you assume in daily life is an illusion born of experience in a region of weak gravity. The universe, in its extremes, does not share your intuitions. Time is as elastic as space, responding to mass, energy, and motion. The implications extend beyond black holes themselves. Every massive object exerts some influence on temporal flow, however subtle. Time is never uniform. It is a landscape warped by every mass in the cosmos. Your measurements, your perception of events, and your assumptions about sequence are always locally constrained, conditional upon your position in space-time. The further you move into extremes, into the deep gravity wells of neutron stars, near black holes, or even the cumulative effect of galactic mass, the more fragile becomes the notion of a universal temporal rhythm. You inhabit a universe where time is no longer absolute, where seconds can stretch into centuries, where cause and effect lose their global meaning. A black hole is a magnifying lens on the elasticity of time, a region where reality itself demonstrates that the flow you rely upon is local, not universal. The river of time is not constant. It bends, stretches, and warps along the contours of gravity. The uniformity you assume is an artifact of weak fields and ordinary scales, not a feature of the cosmos itself. The horizon. You can never cross light, has a finite speed, and this sets a limit on observation. Yet around a black hole, an event horizon forms, a boundary beyond which no signal escapes. You may imagine falling through, but the horizon ensures that what happens beyond it is causally disconnected. There exist regions of the universe that are forever beyond your reach, where events unfold without any impact on your reality. Every measurement you make, every observation you trust, depends on information traveling to you via light or other forms of radiation. This flow of information defines what is real for you. The event horizon imposes a strict limit on that flow. Inside it, no signal can emerge. Events beyond this boundary continue to occur. but they are completely detached from the observable universe. You cannot measure them, predict them, or influence them. They exist, yet their existence has no causal connection to your reality. This disconnection is absolute. Even if you could reach the edge, even if you could hover at the brink, every particle of light or radiation that originates within the horizon is stretched, red-shifted, and trapped by gravity. It asymptotically approaches infinite wavelength, vanishing from your capacity to detect. The universe effectively erases information from your perspective. You witness only the consequences outside the horizon, but the events themselves remain unknowable. This is not a limitation of technology or perception. It is a limitation of physics itself. The horizon also illustrates the relativity of experience. From a distant viewpoint, an object falling toward the black hole appears to slow, frozen in time at the horizon. Signals from its final moments take longer and longer to reach you, stretching into an effective eternity. Yet, from the object's own perspective, time continues normally, and it crosses the boundary without pause. The same event is experienced in radically different ways depending on your position in space-time. There is no universal now, no shared temporal frame. Your reality ends at the horizon, while another sequence of events proceeds beyond it in complete isolation. This boundary is not merely theoretical. Observations of accretion disks around black holes, jets of material accelerated to near-light speeds, and the warping of surrounding space-time all confirm that such horizons exist. They are defined by precise gravitational conditions, measurable, predictable, and consistent with Einstein's equations. The horizon is a real, observable phenomenon, yet it simultaneously represents the ultimate limit of observability. It is a region defined by absence, an absence of outgoing information, an absence of causal connection. The horizon also forces reconsideration of fundamental assumptions about determinism. Events inside the horizon may follow physical laws perfectly, yet they are permanently hidden from external observation. Any prediction about them is necessarily statistical, inferred from boundary conditions, and incomplete. You inhabit a universe where parts of reality are effectively quarantined. The completeness you assume in your measurements, the ability to understand the cosmos from your vantage point, is an illusion imposed by causally accessible regions. Beyond the horizon, knowledge is inherently impossible. Moreover, the concept of isolation at a horizon is not restricted to black holes. Cosmological horizons, defined by the finite age of the universe and the speed of light, create analogous limitations on what can ever be observed. Galaxies sufficiently distant are already receding faster than light can traverse the expanding space. Their events, like those inside a black hole's horizon, are causally disconnected from you. The universe is populated by domains that you will never reach, never witness, and can never affect, all coexisting alongside the reality you inhabit. The horizon is both a boundary and a revelation. It shows that the universe contains regions that are fundamentally inaccessible, where sequences of events unfold independently of you. Space is not continuous in its causal influence. It is compartmentalized, divided into observable and unobservable domains. The edge of reachability is determined by physical law, not by imagination or will. What lies beyond is real, yet entirely disconnected from your experience. In confronting the event horizon, you are forced to recognize a profound structural limitation in reality. Observation, interaction, and influence are not universal. Some regions of existence unfold in total isolation, forever disconnected from your measurements, forever immune to your influence. The universe, in this sense, is not just vast. It is partitioned into domains of certainty and domains that remain permanently unknowable. Cosmic inflations, lingering shadow. You assume the universe expanded steadily from its origin. Instead, it underwent a brief period of exponential growth, smoothing irregularities, yet leaving subtle imprints in the cosmic microwave background. Inflation implies regions of space were once in contact, but are now impossibly distant. The echoes of that early expansion persist, visible as anomalies in a universe that should otherwise be uniform. For most of human history, you might have imagined the cosmos as expanding gradually, a steady stretching of space that preserves continuity and order. Observations of galaxies moving apart, combined with the remnant glow of the Big Bang, seemed consistent with this picture. Yet in the 1980s, theoretical models suggested a startling alternative. In the first fraction of a second, the universe expanded exponentially, increasing in size by a factor that defies intuitive scale. A region smaller than a proton ballooned to dimensions vastly exceeding what we can observe today. The smoothness of the cosmic microwave background is not simply a coincidence. It is a fossilized signature of this extreme, ephemeral inflation. Inflation explains one of the most confounding aspects of cosmology. Why regions of the sky separated by billions of light years share almost identical temperature and density. Without inflation, these regions could never have communicated, and yet their properties are strikingly uniform. The mechanism that smoothed the early universe operated faster than light, stretching space itself, rather than moving signals through it. Causality, as normally understood, is locally violated, not by any object moving faster than light, but because space expanded faster than any information could traverse it. The universe, in that moment, became a domain where intuitive notions of connection and interaction no longer apply. Subtle traces of this violent expansion remain. Measurements of the cosmic microwave background reveal anomalies, small fluctuations in temperature and polarization that persist beyond statistical expectation. These are the fingerprints of the quantum fluctuations that were stretched across immense scales during inflation. Tiny irregularities, magnified by exponential growth, became the seeds for galaxies and clusters. What appears orderly now is the outcome of a profoundly chaotic beginning, encoded in a pattern that is visible only through precise instruments. The implications extend further. Inflation implies that the universe you observe is part of a much larger expanse. Regions beyond the observable horizon may have experienced inflation differently, or not at all, creating domains fundamentally disconnected from your observations. The cosmos is likely far vaster than the light you can see, containing structures and events forever inaccessible. Your perception of uniformity is contingent upon the limits of what has reached you. Beyond those limits, the universe may be heterogeneous, governed by conditions you can neither measure nor influence. Moreover, inflation introduces profound questions about the nature of reality itself. If exponential growth was driven by a field of energy inherent to space, then the vacuum of the early universe possessed properties radically different from those you experience today. The laws of physics in that moment, although compatible with your measurements, now were applied to a space-time in a state of extreme expansion and energy density. The universe you inhabit is the survivor of an initial process that amplified microscopic fluctuations into the scaffolding of galaxies and voids. The apparent order you see is the consequence of a violent, transient mechanism operating at scales and speeds far beyond comprehension. Every galaxy, every cluster, every filament of the cosmic web is a relic of that brief inflationary period. The patterns of large-scale structure reflect the memory of a universe that grew incomprehensibly fast, leaving behind the illusion of uniformity. Space is smooth and continuous only because it was violently stretched, not because order emerged naturally. The expansion you experience as gradual is a slow echo of a process that was once far beyond ordinary intuition. The lingering shadow of inflation is a reminder that your understanding of time, space, and causality is provisional. What seems natural and continuous is in fact the product of a period in which space-time itself behaved in ways that defy ordinary experience. Regions of the cosmos that appear unreachable today were once intimately connected. Patterns you observe as regular are the magnified consequence of quantum fluctuations. The universe you inhabit is structured by an epoch so extreme that its effects remain visible billions of years later, challenging your assumptions about scale, continuity, and the limits of observation. Inflation leaves a persistent tension. The universe is both familiar and alien, orderly and chaotic, local and cosmically fractured. The shadow of that initial growth is written into the very structure of reality, and every observation you make is mediated by a past that stretched space into a form that is simultaneously comprehensible and profoundly unsettling. The multiverse, in our pure measurements, you experience a single reality, continuous and singular. Yet, inflationary models suggest that our universe may be one of countless others, each with different physical laws. The evidence is indirect. Statistical anomalies in the cosmic microwave background. But the implication is unavoidable. Reality might extend beyond every horizon you can ever see, into domains fundamentally disconnected from observation. From your perspective, the cosmos appears boundless, yet unified. The laws of physics are consistent, the constants of nature predictable, the motions of galaxies follow coherent patterns. This apparent uniformity forms the basis for every calculation, every prediction, every understanding of cosmic evolution. Yet if inflation continues in distant regions beyond our observational reach, separate pocket universes may emerge, each expanding independently, each insulated from causal contact with our own. What you consider universal may, in fact, be local, a single domain among an infinity of others. The statistical anomalies in the cosmic microwave background are subtle but significant. Tiny variations in temperature and polarization cannot be fully explained by local processes. Some models suggest these irregularities could be signatures of collisions or interactions with regions beyond our observable universe. If so, you are not measuring only your own cosmic neighborhood. You are glimpsing the shadows of other universes, imprinted faintly on the relic radiation that has traveled 13.8 billion years to reach your instruments. The patterns are small, almost imperceptible, yet they point to structures beyond any direct observation, hinting at a reality far larger than the one you inhabit. This realization undermines assumptions about singularity and continuity. Your reality, experienced as coherent and self-contained, may be an arbitrary fragment of a vastly larger ensemble of domains, each with different laws, constants, or even dimensionality, a universe in which gravity is stronger, where light behaves differently, where atomic structure cannot exist, may coexist alongside the one you know. You can never observe these regions directly. Their existence is inferred, not seen, and their properties may be fundamentally incompatible with any experience you could have. The implications extend to causality and probability. If multiple universes exist, then every event in your domain is part of a larger statistical ensemble. What you perceive as chance, coincidence, or inevitability may be contingent not only on local conditions, but also on the broader landscape of universes, where every possibility plays out somewhere. The certainty you attribute to physical law is relative to your domain. In a neighboring universe, the constants could produce entirely different outcomes, where your existence would be impossible. Reality, in this context, is both richer and more fragile than your perception allows. Yet the multiverse is fundamentally inaccessible. No experiment, no signal, no observation can traverse the boundary between domains. You can only infer their presence through subtle statistical patterns, through the necessity of models that extend beyond your horizon. The evidence is indirect, probabilistic, and unsettling in its implications. A reality larger than observation, where domains exist that cannot be influenced, measured, or understood in full. Your measurements are necessarily local, a sampling from a single bubble in a potentially infinite foam of universes. This concept forces a rethinking of scale and relevance. The universe you inhabit, though vast by human standards, may be an infinitesimal fraction of reality. Galaxies, clusters, and filaments are organized according to laws that may be idiosyncratic to your bubble. Observational cosmology, even at its most precise, can only map a region limited by light speed and time. Beyond that boundary, other realities may evolve independently, forming structures, histories, and causal chains that will never intersect with yours. In confronting the possibility of a multiverse, you are forced to recognize a fundamental limitation in comprehension. Your reality is coherent and complete only relative to the region you inhabit. Beyond your horizon, physics may operate differently. Causality may be rewritten, and what you consider inevitable may be an artifact of local conditions. The universe is no longer a single entity to be understood in totality. It is a fragment of a larger, unobservable ensemble, a shadowed subset of a reality that cannot be fully grasped. The multiverse is not a speculation. It is a logical extension of observations, a consequence of inflation and the anomalies embedded in the cosmic microwave background. Reality may extend into regions that are forever disconnected from perception, where events unfold independently of every measurement you make. You are, in effect, confined to a single bubble in a vast, incomprehensible expanse of existence, surrounded by domains you can never enter, observe, or influence. The scope of what is real is therefore both immense and fundamentally inaccessible, leaving your understanding provisional, local, and incomplete. Neutrinos that pass through everything. Particles pass through your body constantly, yet you never notice. Neutrinos traverse matter almost effortlessly, interacting so rarely they are effectively invisible. Their omnipresence, undetected yet persistent, demonstrates that existence is layered with phenomena beyond sensory perception, shaping events without leaving traces detectable by intuition. Every second, trillions of these particles pass through you, your walls, and every object around you. You do not see them, hear them, or feel them. No sense you possess can detect their passage. Yet they exist, carrying energy, momentum, and information across immense distances. Most originate from the sun, produced in nuclear reactions at its core. Others are the result of distant supernovae, cosmic rays, or exotic astrophysical processes. The universe, in its continuous activity, saturates your immediate surroundings with particles that are simultaneously real and imperceptible. Their invisibility is not a limitation of technology, but a fundamental property of their interaction. Neutrinos interact via the weak nuclear force, one of the four fundamental forces, which governs only certain types of particle decay. Unlike electromagnetic or gravitational forces, which influence matter continuously and noticeably, the weak force acts so subtly that for every trillion neutrinos passing through the Earth, only a handful collide with atomic nuclei. Observation requires enormous detectors buried deep underground, shielded from cosmic interference. In ordinary life, these particles pass through you, and the fact that you remain oblivious is not an accident. It is intrinsic to their nature. Neutrinos reveal that existence is layered. The reality you perceive, atoms, molecules, light, sound, is only one level. Beneath and beyond that level are phenomena that continuously influence, traverse, and shape matter without ever manifesting directly. The mass, energy, and motion of neutrinos collectively affect the universe. They carry away energy from stellar cores, influence the formation of elements, and even shape the evolution of galaxies over cosmic time. You live in a universe structured not only by what you observe, but also by entities whose presence is inferred from effects too subtle for immediate perception. The production of neutrinos is ongoing and pervasive. Every fusion reaction in stars generates vast numbers, and yet the particles move at nearly the speed of light, passing through intervening matter as if it were a ghostly sieve. Supernovae release intense bursts that flood the galaxy. Earth itself generates neutrinos from radioactive decay in its interior. The universe is not empty, even where your senses perceive emptiness. It is threaded with invisible currents that leave no sensory trace but carry energy across incomprehensible scales. This persistent invisibility challenges assumptions about causality and interaction. Events that seem isolated, localized, or self-contained are subtly connected to vast, distant processes. The sun's core, for example, produces neutrinos whose passage through your body is entirely unnoticed. Yet those same reactions sustain life by supplying energy to the surface of the Earth. A direct line of influence exists, but one that bypasses ordinary perception. Reality is not limited to what interacts visibly. It extends to processes that leave almost no trace, yet shape outcomes deterministically. Furthermore, neutrinos are sensitive to conditions that you cannot detect otherwise. They oscillate between types as they travel, a process that reveals the mass of the particle and hints at physics beyond the standard model. Tiny shifts in their behavior encode information about distances, densities, and energies across the universe. They are messengers that pass through matter and space, imperceptible yet laden with knowledge, silently recording the structure and dynamics of reality in ways that light cannot. The omnipresence of neutrinos underscores the incompleteness of intuitive observation. You inhabit a reality where trillions of particles traverse you unnoticed, where invisible currents shape the cosmos and connect distant processes in imperceptible ways. Your senses capture only a fraction of existence. Beyond the visible and tangible lies a universe of subtle, persistent influence, a domain in which phenomena operate continuously and deterministically without ever manifesting to perception. In that sense, the world you experience is only a partial map of reality. The full terrain includes layers that are constant, measurable, and essential, yet forever hidden from ordinary awareness. Quantum superposition. In the macroscopic world, objects appear well-defined. A chair occupies a single place. A cup exists in one state. At quantum scales, particles occupy multiple states simultaneously until measured. If this behavior underlies reality, then determinacy is an illusion, and the world you perceive may be only one realization among countless possibilities existing simultaneously. You move through your room, assuming each object has a fixed position, a defined state and a predictable behavior. Classical physics supports this intuition. Forces act continuously. Masses occupy single locations, and events unfold in a consistent sequence. Yet, at the subatomic level, reality is profoundly different. Electrons in an atom do not inhabit a single orbit. They exist as a cloud of probabilities, a superposition of locations and energies. Only when interaction or measurement occurs does the particle collapse into a definite state. The universe at its foundation is fluid, not fixed, a landscape of potentialities rather than certainties. This principle is not limited to microscopic particles in isolation. Experiments have repeatedly demonstrated superposition across increasingly complex systems. Atoms, molecules, and even small clusters of atoms have been placed in states that exist simultaneously in multiple configurations. These superpositions are fragile, easily disrupted by interaction with the environment, yet they reveal that the classical determinacy you rely upon is emergent, not fundamental. The world of everyday objects is built atop a substrate in which multiplicity and indeterminacy are intrinsic. If the quantum description of matter applies universally, then the apparent definiteness of your surroundings is contingent upon observation and interaction. Every object, from the floor beneath you to the cup on your desk, is composed of particles in potential states, only one of which manifests to your senses at any moment. Your perception collapses possibilities into a coherent reality. Yet countless alternative arrangements, equally real at the quantum level, remain unobserved. Determinacy is not a universal law, but an emergent pattern produced by the interaction of countless probabilistic events. This has profound implications for causality and identity. If the universe at its foundation consists of simultaneous possibilities, then the chain of cause and effect you experience is only one among an uncountable number of sequences. Each decision, each motion, each collision of particles could have collapsed differently, producing alternate outcomes that are physically real at the quantum level, yet forever inaccessible to you. The continuity and coherence of your world are statistical artifacts, stabilized by decoherence, but the underlying potentiality persists beneath the surface of every moment. Superposition also challenges notions of separability. Particles in superposed states can be entangled, meaning the state of one particle is instantaneously correlated with another, regardless of distance. The determinate world you perceive is therefore not only an emergent effect of observation, but also a network of correlations that are constantly mediated by underlying quantum probabilities. Reality is less a collection of individual objects and more a tapestry of potential outcomes, interwoven in ways that are invisible and inaccessible to direct experience. Experiments with quantum interference reinforce this perspective. Particles passing through multiple paths simultaneously produce patterns that cannot be explained by classical trajectories. The macroscopic objects you consider stable and singular are composed of layers of such quantum behavior. The chair you sit on, the cup in your hand, the light reflecting from a window, all exist atop a foundation of superposition, a substrate where every constituent has, at least briefly, multiple potential realities. Even if practical observation and decoherence mask these possibilities at human scales, the universe itself contains them. Every interaction you witness is a particular realization of underlying potentialities, selected from a vast quantum landscape. Your experience of a singular, well-defined world is contingent, ephemeral, and constructed from probabilities that exist simultaneously, yet invisibly. Reality, in this sense, is far more complex than your perception allows. A multitude of coexisting states, of parallel potentialities, all layered beneath the coherent world you inhabit. The implications are quietly unsettling. What you consider determinate is emergent, dependent on interaction, and contingent upon measurement. Beneath the surface of apparent stability lies a foundation of multiplicity, a reality in which countless possibilities coexist, only one of which manifests to perception. The world you experience is a singular thread in a vast underlying weave of potentialities, and the stability you trust is only one outcome among many, selected silently, probabilistically, and invisibly. Entanglement. Across space. You experience separation as fundamental. What occurs here is independent of what occurs far away. Quantum entanglement defies that assumption. Paired particles exhibit correlations regardless of distance, suggesting instantaneous connections that contradict classical notions of causality. Reality is entangled, and locality is not guaranteed. Your intuition rests on the idea that events in one place cannot immediately affect events elsewhere. Objects occupy positions in space, signals travel at finite speeds, and causes precede effects within a clearly defined framework. Entanglement, however, shows that two particles can become linked such that the measurement of one instantaneously determines the state of the other, regardless of the spatial distance separating them. A correlation emerges that is independent of time, distance, or conventional channels of communication. This is not a hypothetical phenomenon. Experiments stretching over kilometers, using photons, electrons, and atoms, have repeatedly confirmed that entangled particles behave in ways incompatible with classical locality. Bell's theorem provides a mathematical framework demonstrating that no local hidden variable theory can account for the observed correlations. Nature does not operate according to your expectation of independent, locally determined events. It is fundamentally non-local, revealing connections that span space instantaneously. The consequences are profound. You perceive the world as composed of separate objects, interacting through forces transmitted across space. Entanglement implies that this separation is, at a fundamental level, an approximation. Particles are not isolated. Their states can be intertwined with distant partners, forming a network of correlations that exist across the universe. A change in one particle is reflected in its entangled counterpart immediately, with no discernible medium or delay. Space, in this context, is not an absolute barrier to influence or coherence. Entanglement challenges assumptions about information and causality. No usable signal travels faster than light, so relativity remains intact, yet the correlation itself exists beyond conventional spatial constraints. You cannot predict the outcome of a single measurement, but once one is observed, the other's state is determined. Reality is coordinated in ways that do not align with the intuitive notion of separate locations or independent events. Even in the absence of direct interaction, the universe maintains these connections across vast distances, suggesting a fundamental interdependence at the quantum level. These correlations extend beyond pairs. Large systems can become entangled, forming networks where the state of one part depends on the state of many others. Decoherence often suppresses these effects in macroscopic objects, making entanglement subtle and indirect in everyday experience. Yet, at the microscopic scale, it is pervasive. This universe is a lattice of instantaneous, non-local relationships, and your perception of isolated entities is emergent, a product of interaction with the environment that masks deeper connectivity. The implications also extend to measurement and knowledge. Observation of one particle collapses the combined state of the entangled system. The act of measurement does not simply reveal reality. It participates in shaping it. Localized perception is thus a partial view of a system whose underlying correlations are distributed across space. Your measurements capture only a fragment of a connected reality, leaving an unseen network of dependencies beyond your immediate access. Entanglement further blurs the distinction between cause and effect. If two entangled particles are separated by light years, the state of one is correlated with the other instantly. No sequence of intermediate interactions is required. The universe allows for simultaneous coordination that does not obey classical, temporal order. Separation is a useful approximation for macroscopic interactions, but at the quantum level, it is provisional, not fundamental. In this sense, reality is not compartmentalized. Your assumption that influence diminishes with distance fails at the quantum scale. Objects, events, and measurements are embedded in a web of correlations, a lattice of connectivity that spans space itself. Locality, which seems self-evident in daily experience, is contingent and emergent. The deeper structure of reality is a network of entangled states, silently linking distant regions and demonstrating that the universe is far more interconnected than perception suggests. The universe you inhabit appears divided, discrete, and separable. Entanglement reveals that this division is superficial. Beneath the apparent boundaries of space, particles maintain instantaneous, invisible connections. Reality is not fragmented into independent locations. It is fundamentally relational, woven together across distances, and your experience of separation is only an emergent approximation. The universe's missing mass. You expect that the visible universe accounts for most matter. Observations of galaxy clusters show a severe discrepancy. What is measured through gravity is far greater than what can be seen. The majority of mass is invisible, shaping motions and structures without ever being detected directly. Your perception is of a universe that barely exists as it appears. When you look at a galaxy, the stars, and dust seem to provide an intuitive explanation for its behavior. Newtonian gravity predicts that stars on the outskirts should orbit more slowly than those near the center, where most visible mass resides. Yet measurements show the opposite. The outer stars maintain speeds that imply a gravitational pull far stronger than what the luminous matter can supply. The universe you observe is incomplete. Most of its content is hidden from every sense and every optical instrument. This invisible mass, known as dark matter, does not emit or absorb light. It does not interact with ordinary matter except through gravity. Despite its elusiveness, its presence is unequivocal. Gravitational lensing, where light from distant galaxies is bent by intervening mass, confirms that clusters contain far more matter than meets the eye. The path of every photon is influenced not only by what you can see, but also by what you cannot. The universe, in effect, is structured according to forces that are invisible to perception, yet perfectly measurable through their consequences. The scale of the discrepancy is staggering. Ordinary matter, everything you can touch, measure, and detect, accounts for roughly 5% of the total mass energy content of the cosmos. Dark matter constitutes around 27%. The remaining 68% is dark energy, the entity driving cosmic acceleration. What you perceive as reality, the planets, stars, galaxies, and clusters, is only a fraction of what physically exists. The bulk of the universe is a hidden framework, silently shaping motion, structure, and evolution on scales both local and cosmic. This unseen mass is not simply a subtle addition to gravity. It defines the architecture of the cosmos. Galaxies form along filaments of dark matter, tracing its invisible scaffolding. Clusters are bound together by halos of unseen material, dictating the flow of intergalactic gas and the dynamics of star formation. Without dark matter, the universe would look dramatically different. Galaxies would disperse, clusters would not cohere, and the large-scale cosmic web would fail to form. The cosmos you inhabit is fundamentally dependent on the presence of mass you cannot detect directly. Attempts to detect dark matter particles have so far failed. Experiments using underground detectors, sensitive to interactions with ordinary matter, have found no definitive evidence. This is consistent with its defining property. Dark matter interacts primarily through gravity. You can infer its presence, measure its effect, and predict its influence with precision. Yet the particles themselves remain hidden. The reality you perceive is an interface. It is a map of visible matter imposed upon a substrate that is mostly invisible. The existence of missing mass also challenges assumptions about locality and measurement. What you observe in a cluster of galaxies is governed not by the sum of visible objects, but by an unseen mass distributed across the system. Your intuition, which equates existence with visibility, fails at cosmic scales. Forces operate independently of perception, and the universe obeys laws that transcend the limitations of your instruments and senses. In confronting the missing mass, you are confronted with a universe both familiar and alien. Gravity behaves predictably, yet the substance that generates it remains undetectable. Galaxies move as if guided by a hand you cannot see. Clusters rotate and cohere under the influence of matter you cannot touch. Your perception of solidity and substance is provisional, a partial view of a cosmos where most of what exists escapes direct observation. The visible universe is only a surface phenomenon. Beneath it lies an invisible scaffolding of matter that dominates every structure, every motion, and every cosmic interaction. Reality is largely unseen, and your perception, trustworthy in the small scale of immediate experience, fails to capture the majority of what is physically present. The universe as it appears to you is, in fact, a fraction, an outline imposed on an overwhelming hidden reality, and the majority of its mass exists in a form that you will never observe directly. The arrow of time. You assume time flows in one direction, from past to future. Yet the fundamental laws of physics are time-symmetric. The asymmetry you observe, the flow from order to disorder, is a result of initial conditions rather than law. Time's arrow emerges as a statistical consequence, leaving you to confront that your experience of causality is contingent, not absolute. Every process you witness appears directed. Ice melts, stars age, objects decay, and memories accumulate. You interpret these observations as evidence of an irreversible progression. Events unfold, causes precede effects, and the past is fixed while the future is open. Yet the underlying equations of mechanics, quantum theory, and even relativity do not prescribe this direction. They are indifferent to past or future. They describe evolution that could run forward or backward with equal validity. The sense of temporal flow emerges not from fundamental law, but from boundary conditions set at the beginning of the universe. This boundary, the low entropy state of the early universe, is the source of the asymmetry you perceive. At the moment of the Big Bang, matter and energy were arranged in an extraordinarily ordered configuration. From that initial condition, statistical mechanics dictates that entropy, the measure of disorder, will increase. Systems evolve toward more probable configurations. The direction of time, the arrow you experience, is therefore not intrinsic to physics, but emergent from probability. Your perception of causality is a consequence of this statistical bias, not a universal truth. The implications are subtle yet profound. If the laws themselves are reversible, then in principle, time could run backward. A system of particles obeying Newtonian mechanics could retrace its trajectory if initial velocities were reversed. The melting ice cube could spontaneously refreeze, a broken glass reassemble, a past reemerge from the future. These outcomes are overwhelmingly improbable, but they are permitted by the fundamental dynamics. The direction you experience is contingent, a consequence of conditions far beyond observation or influence. Time's arrow is also scale-dependent at microscopic levels. Interactions are largely reversible. Particles collide, scatter, and evolve according to laws that do not distinguish past from future. Irreversibility appears statistically only in aggregates of countless particles and is reinforced by interactions with the environment. Your experience of a continuous, unidirectional flow is an emergent phenomenon, a macroscopic illusion grounded in the statistical behavior of underlying reversible processes. Reality is therefore layered, deterministic at the fundamental level, probabilistic at the intermediate, and apparently irreversible at the scale of perception. Furthermore, the arrow of time is entwined with memory and information. You retain traces of the past, but none of the future. This asymmetry is not mandated by physics. It is a consequence of the low entropy starting point and the statistical unfolding of matter. Observers, recording events and processing information, are themselves embedded in a system that evolves toward disorder. The continuity and coherence of memory and causality are emergent features of statistical processes, not absolute properties of the universe. Even the flow of cosmological time is contingent. Expansion of space, the evolution of galaxies, and the eventual heat-death of the universe are all governed by conditions set at the beginning. The direction in which stars age and black holes evaporate reflects the initial low entropy state. Were the universe arranged differently at its origin, your perception of past and future could be inverted, or perhaps meaningless. The arrow of time is provisional, an emergent orientation arising from a cosmic contingency. You inhabit a universe where the perception of sequential, irreversible events is not dictated by fundamental law. Order transitions to disorder because it began in a state of extreme order. Your experience of causality, of progress, of past and future is a product of initial conditions amplified by statistical mechanics. The universe is, in principle, reversible. The direction of time is not a universal feature, but a consequence of contingent circumstances. The arrow you trust is provisional, emergent, and ultimately a reflection of the deep improbability of the conditions from which it began. Cosmic acceleration. Without explanation, galaxies recede faster than expected. The acceleration cannot be attributed to ordinary matter or gravity as we understand it. Dark energy is inferred to account for the discrepancy, yet its nature remains unknown. Observation confirms expansion. Theory struggles to explain its driver. You inhabit a cosmos propelled by something fundamentally uncharacterized. When Edwin Hubble first measured the recession of galaxies, he revealed that the universe is expanding. It seemed logical to assume that this expansion would gradually slow under the influence of gravity. Matter exerts a pull, and over cosmic timescales, it should decelerate the rate at which galaxies move apart. Yet observations of distant supernovae in the late 20th century contradicted this expectation. Galaxies were not merely receding, their separation was accelerating. Space itself stretches at an increasing rate, driven by a force or energy that eludes precise identification. This acceleration is subtle, yet measurable. Light from distant supernovae appears fainter than expected, implying that the sources are farther away than predicted by models of decelerating expansion. The cosmic microwave background provides independent confirmation. The large-scale geometry of space and the distribution of matter reflect the influence of a pervasive, repulsive component. This evidence does not rely on speculative constructs. It emerges from precise, reproducible measurements that reveal a persistent, unexplained acceleration. The inferred presence of dark energy is not a theoretical convenience, but a necessity. Ordinary matter, radiation, and even the gravitational influence of unseen dark matter cannot account for the observed dynamics. To reconcile measurements with known physics, cosmologists introduce a component with negative pressure, something that pushes space itself outward. Yet the nature of this entity is entirely unknown. It does not emit or absorb light, interact with particles in any familiar way, or leave a direct trace. You infer its existence only through its effect on the fabric of the cosmos, a silent, pervasive driver of expansion that escapes direct observation. The implications are profound. Space is not passive. It possesses a property that actively alters its own dynamics. Galaxies are carried apart not by motion within space, but by the expansion of space itself, accelerated by a source you cannot identify. This phenomenon challenges intuitive assumptions about the universe. You imagine forces acting between objects, but here the force is distributed, intrinsic to space, and fundamentally inscrutable. The very stage upon which events unfold is actively shaping the evolution of everything you observe. This acceleration also carries a temporal dimension. Extrapolating backward, the universe must have transitioned from a decelerating phase dominated by matter to an accelerating phase dominated by dark energy. The shift is subtle in human terms, but profound on cosmic scales. The structures you observe, galaxies, clusters, filaments, formed in a universe governed by forces that are now being overwhelmed by an unknown component. The universe you inhabit exists in a regime where the rules of large-scale evolution are increasingly dominated by something you cannot characterize. Your perception of stability and predictability is further undermined by the magnitude of the effect. The acceleration is persistent, extending into the future indefinitely, as far as current observation allows. Every galaxy outside your local group will eventually recede beyond the limits of detectability. Light from distant objects will never reach you. The observable universe will shrink in practical terms, even as space continues to expand. The driver of this expansion remains invisible, its nature fundamentally unknown, yet its influence is absolute and inevitable. The phenomenon demonstrates a disconnect between observation and understanding. You measure, map, and predict, yet the underlying cause of cosmic acceleration remains unexplained. Reality behaves consistently, obeying measurable laws, yet those laws include a component whose essence eludes comprehension. You inhabit a universe propelled by a force that cannot be seen, touched, or measured directly, a force that is necessary for cosmological models, yet wholly uncharacterized. The cosmos unfolds according to principles you can measure but do not yet understand, reminding you that observation can be complete while explanation remains forever incomplete. The quantum, foam beneath reality. You believe space is smooth and continuous. At the smallest scales, space-time is turbulent, composed of fluctuating quantum foam. These fluctuations are too small to detect directly, but influence particle behavior and gravitational waves. The fabric of reality itself is restless, structured by ceaseless, microscopic chaos. The space around you, which seems uniform and featureless, is in fact a seething expanse of ephemeral disturbances. Quantum mechanics predicts that even in a vacuum, energy fluctuates constantly. Virtual particles blink into existence and vanish within infinitesimal fractions of a second. The vacuum is not empty. It is alive with transient phenomena, creating a restless substrate that underlies every observable interaction. Your perception of emptiness is an artifact of scale. At the Planck length, roughly 10 to 35 meters, smoothness dissolves into turbulence. Gravity, too, is influenced by this foam. The metric of space-time is not static. Tiny fluctuations at quantum scales propagate subtly, perturbing the trajectories of particles and the propagation of light. Gravitational waves, ripples in space-time caused by massive events, must propagate across a medium that is itself jittering at scales far below direct measurement. Even as you observe the steady orbit of planets or the coherent motion of galaxies, these motions are mediated by a substrate of microscopic unpredictability. The apparent stability of macroscopic reality is built atop a foundation that is ceaselessly irregular. The concept of quantum foam emerges from the combination of general relativity and quantum mechanics. General relativity treats space-time as a smooth continuum, deformable by mass and energy. Quantum mechanics, however, insists that no field, no metric, can be completely static. The two principles together imply that space-time is granular at the smallest scales, a landscape of peaks, valleys, and transient fluctuations. What seems continuous is in fact the statistical average of innumerable microscopic disturbances, a macroscopic approximation of a fundamentally restless structure. These fluctuations also influence particle behavior. Virtual particles, born from the foam, contribute to measurable effects such as the Casimir force, a subtle attraction between metal plates in a vacuum. The energy of the vacuum affects the mass of particles and contributes to the cosmological, constant driving cosmic acceleration. Every quantum fluctuation, though ephemeral, has a persistent effect when aggregated across space and time. Reality is, in this sense, not simply a passive stage. It is an active, dynamic field whose microscopic turbulence shapes observable phenomena. The implications extend to the notion of locality. At these scales, space-time itself becomes uncertain. Distances, durations, and trajectories are not precisely defined. The very concept of a smooth, continuous backdrop breaks down. Events that appear localized are in reality situated within a jittering, fluctuating network of space-time. Causality, as intuitively understood, emerges only at larger scales, where the statistical averaging of quantum fluctuations produces a coherent temporal and spatial framework. At its foundation, the universe is probabilistic, restless, and indeterminate. Moreover, quantum foam suggests that even empty regions of the cosmos are structured, not void. Black holes, neutron stars, and cosmic voids all exist atop this turbulent foundation. Gravitational waves, emitted from distant mergers, propagate through a medium that is itself jittering at microscopic scales, implying that the ripples you detect are shaped by a substrate beyond classical intuition. The smoothness of space-time, the apparent continuity of distance and motion, is an emergent illusion arising from the averaging of underlying chaos. Your everyday experience conceals this restlessness. Walking across a room, watching sunlight filter through a window, observing planets through a telescope, you encounter continuity, order, and predictability. Yet beneath every observation lies the seething quantum foam, the probabilistic, fluctuating matrix of space-time itself. Reality is layered. The stable, measurable domain you perceive rests atop a turbulent, ceaselessly dynamic foundation, structured not by permanence, but by ephemeral, unobservable fluctuations that shape every interaction in ways you can infer, but never directly see. The universe is not quiet. Even where nothing seems to exist, it is alive with invisible activity. Space itself is a restless, fluctuating entity. And the solidity, continuity, and smoothness you take for granted are emergent illusions projected from a substratum of microscopic chaos. The fabric of reality is turbulent at its core, and your perception of stability is contingent, provisional, and constructed from the statistical averaging of ceaseless quantum unrest, time dilation in everyday life. You experience seconds and minutes as constant. Yet even on Earth, moving clocks run slower. Gravitational potential alters temporal flow. The effects are subtle, measurable only by precise instruments, but they reveal that every moment you live is slightly shifted from what another observer experiences. Time is personal, not universal. Your daily life assumes a shared rhythm. Clocks tick in unison, schedules proceed, and causal sequences unfold predictably. Yet Einstein's theory of relativity demonstrates that this perception is approximate. Motion and gravity distort time. A clock in motion, relative to you, ticks more slowly than your own. A clock closer to Earth's surface, in a stronger gravitational field, ticks more slowly than one farther away. Even on human scales, these differences, though minute, are real, measurable, and inevitable. The global positioning system provides a tangible illustration. Satellites orbiting Earth experience both gravitational time dilation and the effects of their orbital speed. Engineers must account for these shifts. Without correction, GPS positioning would drift by kilometers each day. Your perception of synchronized time is therefore a construction, corrected for relativistic effects that exist even in ordinary environments. The now you inhabit is not a universal instant, but a personal experience, offset subtly from that of every other observer. These temporal shifts are continuous. Every step you take, every journey you undertake, changes your velocity, and therefore the rate at which your clock runs relative to stationary observers. Every centimeter of altitude introduces a minute difference due to gravitational potential. Time is not a constant backdrop. It is a dynamic, local variable, shaped by motion and mass. What you experience as uniform flow is an emergent illusion, arising from the relative slowness of these effects in familiar conditions. The implications extend to causality and simultaneity. Two events, perceived as simultaneous from one frame of reference, may occur in different sequences from another. Your understanding of what happens now is therefore dependent on your position and motion. The universe has no single, absolute temporal framework. Instead, every observer carries a private arrow of time, slightly diverging from that of others. your experience of causation, what comes before and after, is contextual, anchored in your local space-time. Even at everyday speeds, these effects are measurable. Experiments with atomic clocks flown on airplanes or transported to high-altitude laboratories demonstrate predictable discrepancies. A clock flown eastward around the globe loses nanoseconds relative to a stationary counterpart. A clock at the summit of a mountain gains nanoseconds relative to one at sea level. The differences are imperceptible to human senses, yet they are real, recorded, and repeatable. Each person's experience of elapsed time is therefore a localized phenomenon, shifted subtly by the gravitational landscape and the velocities they traverse. This relativity of time undermines assumptions about a universal present. Your perception of a coherent now is provisional, defined by your trajectory through space-time. Someone moving differently or located at a different gravitational potential inhabits a slightly different temporal frame. There is no absolute simultaneity. Time, as you experience it, is entwined with your environment and your motion. A private rhythm imposed by local conditions rather than a global constant. Moreover, these effects are cumulative. Over days, months, and years, even the smallest differences aggregate. Astronauts orbiting Earth for months age slightly less than people on the surface. Particles traveling near the speed of light decay more slowly than identical particles at rest. The flow of time is a local, variable phenomenon. Your aging, your perception, your measurement of events, all are dependent on your relative motion and gravitational context. You inhabit a universe where seconds are personal, where the continuity of experience is an emergent, relative property. The constancy you take for granted is provisional, contingent on position, velocity, and mass. Every moment you live is already slightly shifted from what any other observer experiences. Time is not universal. It is local, relational, and subtly fractured across the fabric of space-time. The reality you trust as temporally coherent is only a slice, defined by your own path through a continuum that is far more flexible and complex than perception allows. The cold death of the universe. You might assume the universe will endure indefinitely in a stable state. Thermodynamic principles suggest otherwise. Entropy increases inexorably, energy disperses, and stars will fade. The cosmos trends toward uniformity and inactivity, an ultimate equilibrium in which change becomes impossible, leaving the universe as a cold, inert expanse. Every process you observe, from the fusion of hydrogen in stars to the metabolism of life on Earth, is governed by the second law of thermodynamics. Energy is constantly redistributed flowing from high to low concentrations, producing work, motion, and structure. The directionality of these processes defines the arrow of time, the distinction between past and future. Yet this directionality is finite. Energy is not created or destroyed, only transformed. As work is performed, usable energy becomes increasingly dispersed, and the universe inexorably trends toward a state in which no work can occur. Stars, the engines of cosmic structure, provide a vivid illustration. They fuse lighter elements into heavier nuclei, radiating energy into space. Over billions of years, this process converts concentrated mass into dispersed photons, slowly depleting the fuel that sustains fusion. Eventually, stellar remnants will dominate: white dwarfs, neutron stars, and black holes. No new stars will form. The radiant energy that once illuminated galaxies will fade. The cosmos will grow darker, colder, quieter. Energy gradients, which sustain every process, will diminish until the universe reaches near uniform temperature and energy distribution. This ultimate equilibrium, sometimes called heat death, is not dramatic in the human sense. It will not occur suddenly or catastrophically. Rather, it is the gradual fading of difference, the loss of the contrasts that make change possible. Planets will orbit dim remnants. Matter will decay over unimaginable timescales, and even black holes will evaporate via Hawking radiation. The cosmos will exist in a state of near-perfect uniformity, a vast expanse where motion, reaction, and evolution have effectively ceased. The universe you perceive, so vibrant and dynamic, is provisional, a transient configuration in a long trajectory toward inertia. Entropy's increase also carries implications for perception and measurement. Processes that create order, galaxy formation, chemical reactions, life, are temporary pockets of reduced entropy, sustained only by continuous energy input. The universe permits structure and observation only because energy is unevenly distributed. As these imbalances fade, so too does the possibility of organized systems. Observers, including you, are contingent on these temporary gradients. In the distant future, the conditions necessary for measurement, cognition, and perception may vanish entirely. Reality will remain, but its capacity for activity, differentiation, and experience will dissipate. Even the laws of physics, which dictate motion and interaction, operate against this backdrop of increasing entropy. Gravity may pull matter into localized concentrations, yet these too will decay or collapse. Particles decay, nuclei undergo radioactive transformations, and energy is redistributed in ways that smooth out disparities. Over time scales vastly longer than the current age of the universe, every distinction will fade, leaving a homogeneous, cold expanse in which nothing can change, nothing can move, and nothing can be observed in meaningful ways. The cold death of the universe is both inevitable and impersonal. It is not a result of failure or design. It is a statistical consequence of the laws that govern matter and energy, the warmth of stars, the rotation of galaxies, the activity of planets, and the emergence of life are temporary anomalies in a cosmos driven toward uniformity. All that you consider dynamic and significant is ephemeral, a transient fluctuation in a trajectory that ultimately favors stasis and silence. You inhabit a universe that is vibrant only in contrast to its inevitable decay. Every moment of activity, every burst of energy is provisional, fleeting, and ultimately subsumed by the slow, relentless drift toward entropy. In the end, the cosmos will persist only as a cold, dark, and featureless expanse. All differentiation, all change, and all action will cease. The universe as it exists now is merely an intermediate stage, a temporary configuration before the ultimate, eternal equilibrium, a silent, inert, and uniformly cold end that defines the ultimate boundary of cosmic possibility. Cosmic rays from distant catastrophes. Particles constantly bombard you from distant supernovae, gamma-ray bursts, and black hole jets. They traverse light years to reach your position, unaffected by local obstacles. The universe is not insulated. Every location is exposed to distant cataclysms, reminders that your isolation is an illusion, and every region of space is causally connected through invisible flux. You inhabit a region of space that appears quiet and stable. The air in your lungs, the sunlight filtering through windows, the apparent emptiness surrounding you, all suggest separation from distant phenomena. Yet the particles striking your atmosphere betray this illusion. Cosmic rays, high-energy protons, nuclei, and electrons arrive from galaxies, exploding stars, and relativistic jets, carrying the energy of events that occurred millions or billions of years ago. Each particle is a messenger, connecting your local environment to remote, violent processes. The flux of cosmic rays is constant and global. Earth's magnetic field and atmosphere provide partial shielding, deflecting and scattering many incoming particles, yet some penetrate to the surface. Even in the deepest underground laboratories, detectors capture rare events that reveal the persistent presence of these distant energies. Your body, the ground beneath you, and every object in your vicinity are subtly influenced by processes occurring far beyond immediate perception. The universe does not recognize your boundaries. Every location is exposed to the consequences of events across unimaginable distances. These particles are not simply local curiosities. They encode information about the structure and dynamics of their origins. Supernovae accelerate particles to relativistic speeds, imprinting signatures of shock waves and magnetic fields. Gamma-ray bursts, some of the most energetic explosions in the universe, emit particles that travel across intergalactic space, arriving unaltered except for interactions with cosmic magnetic fields. Black hole jets channel matter and energy at nearly the speed of light, spreading energetic particles across vast regions. What you experience as a seemingly empty or safe environment is continuously permeated by this distant activity. Cosmic rays also highlight the interplay between scale and vulnerability. While individual particles carry negligible energy relative to your body, their aggregate flux represents a constant exchange between you and distant astrophysical phenomena. Over geological and evolutionary timescales, they have influenced atmospheric chemistry, mutation rates, and even climate. The apparent stability of your environment masks a subtle, persistent connection to remote cosmic events. Isolation is never absolute. Exposure is unavoidable. And the universe communicates across distances you cannot perceive with ordinary senses. The trajectory of each particle is largely unimpeded by ordinary matter. Even dense objects, mountains, and oceans are effectively transparent at these energies. The arrival of cosmic rays illustrates that distance, mass, and apparent separation do not guarantee insulation from the broader universe. Events millions of light years away produce measurable effects here and now, linking causally distant regions in a web of influence that transcends the intuitive limits of space. The universe is coherent, interconnected, and continuous, even where perception suggests fragmentation. Furthermore, the distribution of cosmic rays reflects the dynamic and chaotic nature of the cosmos. Their directions, energies, and flux vary over time, tracing the evolution of star formation, galactic magnetic fields, and cataclysmic explosions. Observation of these patterns reveals that what appears local is contingent upon processes at scales vastly larger than immediate perception. Every location in the cosmos is embedded within a vast network of energetic influence, in which distant violence resonates silently, yet measurably, at the smallest scales of experience. Your immediate environment, which feels isolated and stable, is therefore penetrated constantly by remnants of extreme, faraway phenomena. Each particle is an emissary of remote cosmic activity, a reminder that your sense of separateness is provisional. Reality is interconnected through fluxes you cannot perceive, and every point in space participates in a network of influence and energy that stretches across galaxies. The cosmos is active, continuous, and inescapably linked, and the quiet moments you inhabit are permeated by the invisible consequences of distant catastrophes. The illusion of spatial continuity. You navigate space as if it were continuous. Yet on quantum scales, space may be discrete, composed of indivisible units. Measurements of gravity and light hint at granularity, suggesting that smooth trajectories are approximations, and continuity is an emergent illusion, not a fundamental property of reality. Your daily movements reinforce the perception of a continuous, unbroken environment. You step across the floor, reach for a cup, or observe the sweep of sunlight across a room. Distances seem divisible without limit, and motion appears fluid. Classical physics treats space as a continuum, an arena in which objects move along defined paths and interactions occur smoothly. Yet the combination of quantum mechanics and general relativity suggests that this intuition breaks down at the smallest scales. Space may be composed of discrete, finite units, each indivisible and separated by a scale beyond direct observation. The Planck length, approximately 35 meters, defines the scale at which this discreteness becomes relevant. At such dimensions, the smooth geometry of space-time dissolves into a lattice-like structure, fluctuating with the activity of quantum foam. Paths that appear continuous at macroscopic scales are statistical averages of underlying stepwise transitions. Light, gravity, and particles propagate not through an infinitely divisible medium, but across a structured network of discrete units, where apparent continuity emerges only in aggregate. Evidence for this granularity is subtle. The behavior of gravitational waves, the propagation of high-energy photons, and limits in the precision of space-time measurements suggest that smooth trajectories may conceal an underlying discreteness. Experiments searching for irregularities in light from distant sources or for minute delays in signals across vast cosmic distances are attempts to reveal the granularity of space. Each null result constrains the scale of these effects, but also reinforces the unsettling possibility. The space in which you live and measure is not fundamentally smooth. The illusion of continuity is a product of scale, a simplification imposed by perception and averaging. This discreteness implies that motion, position, and distance are fundamentally quantized. Objects do not glide through space in infinitely divisible increments. They traverse a lattice of spatial quanta with the apparent smoothness of trajectories emerging from interactions among countless discrete units. Your perception of uninterrupted motion is therefore an emergent phenomenon, a macroscopic consequence of microscopic discontinuity. The coordinates you assign to objects, the paths you calculate for planets or spacecraft, are approximations of a deeper, granular structure that you cannot observe directly. The consequences extend to measurement and causality. If space is quantized, the exact position of a particle or object becomes a statistical property rather than a continuous variable. Precision is limited, and the notion of infinitely divisible distances loses meaning. Even the propagation of light is affected. Photons traverse a lattice that may subtly shift their paths, producing effects only detectable across astronomical scales or with extreme precision. Reality is not a seamless backdrop, but a network of discrete relationships that manifest as continuity only at larger scales. At cosmic scales, this illusion is profound. Galaxies orbit, stars shine, and planets move in apparent precision. Yet their trajectories are fundamentally emergent patterns on a discretized stage. The universe you experience as smooth, ordered, and navigable is underpinned by a substrate of finite units. The space you trust as continuous is a coarse-grained approximation of a reality that is granular, stepwise, and probabilistic. You inhabit a world in which continuity is provisional. What appears as smooth motion, seamless distance, and unbroken space is an emergent artifact, a statistical averaging of discrete quanta. The universe beneath perception is discontinuous, granular, and fundamentally different from experience. Every path you trace, every distance you measure, every trajectory you assume is a simplified projection of a lattice-like reality. And the smooth space you trust is not a fundamental property, but an emergent illusion. The persistence of black hole. Information. You assume that anything swallowed by a black hole is lost forever. Quantum theory challenges this. Information is preserved, somehow encoded in subtle radiation or at the event horizon. Reality safeguards its history in inaccessible ways, implying that loss is apparent, not absolute, and knowledge can be hidden in the fabric of space-time itself. Black holes are regions where gravity is so strong that escape is impossible once an object crosses the event horizon. Classical physics suggests that all matter entering a black hole is irretrievably destroyed, its characteristics obliterated beyond any measurement. The idea is simple. A star collapses, matter accumulates, and the interior becomes inaccessible. Any information about the original structure seems lost, erased from the observable universe. Yet the principles of quantum mechanics insist that information cannot be destroyed. The universe, at a fundamental level, preserves correlations, probabilities, and histories, even in extreme environments. This tension between classical black holes and quantum theory defines the information paradox. When Stephen Hawking first calculated black hole radiation, he demonstrated that black holes emit thermal radiation due to quantum effects near the event horizon. This radiation appears entirely random, suggesting that the information about what fell into the black hole might escape only as statistical noise, obliterated in translation. Yet the laws of quantum mechanics assert that randomness cannot erase history. If information is truly conserved, it must persist somewhere, encoded in a form that eludes straightforward observation. Current theoretical models propose that this information may be imprinted on the event horizon itself, a holographic record of everything absorbed by the black hole. The concept is radical. A two-dimensional surface could encode the three-dimensional content that once fell inside. Reality, in this view, protects history by storing it in ways that are inaccessible to direct measurement. You cannot peer inside a black hole, yet the correlations, the traces of past states, exist in the structure of space-time, hidden but not destroyed. The universe is both faithful and secretive, preserving order in ways that defy conventional perception. The persistence of information also has profound implications for causality and determinism. If information is never lost, then the evolution of a black hole, including its formation and evaporation, is in principle reversible. What seems like an endpoint, a singularity, a region of absolute destruction, is actually part of a larger information-preserving process. The universe maintains coherence even where extreme conditions appear to obliterate it. Knowledge is obscured, not annihilated, and every state of matter has a potential imprint somewhere, waiting to be decoded through physics you cannot yet perform. Observational consequences are subtle. Hawking radiation is minuscule, almost undetectable for stellar mass black holes. Information, if encoded in this radiation, is spread across countless quanta over vast periods. The recovery of this history is impractical, perhaps impossible in practice, but the principle remains. Reality does not forget. The paradox emphasizes that your perception of irreversible loss is provisional. What seems destroyed is merely hidden within deeper layers of space-time, structured in ways that challenge intuition, measurement, and understanding. The information paradox also underscores the fragility of assumption. You may equate inaccessibility with destruction, absence with non-existence. Black holes demonstrate that reality operates under principles that preserve history, even when human measurement cannot. The universe is a repository of its own past. Encoding knowledge in forms beyond direct observation. Your experience of loss, of events disappearing beyond your reach, is limited by practical capability, not by the universe's willingness to conserve information. Every black hole thus becomes a testament to the hidden order of the cosmos. Matter can vanish from sight, yet its information persists, embedded in subtle correlations in the event horizon or in the statistical structure of radiation. The universe records its own history in inaccessible ways, reminding you that reality is more persistent than perception suggests. What is lost to view may never truly disappear. The past remains, woven into the fabric of space-time, hidden yet preserved, challenging assumptions about permanence, causality, and the ultimate reach of observation. The cosmological constant problem. You take for granted that energy scales in physics are consistent. Calculations of vacuum energy suggest a magnitude vastly larger than what is observed through cosmic acceleration. Nature reconciles the difference, but the mechanism is unknown. The universe tolerates a discrepancy between theory and measurement that is unnervingly large, hinting at unknown principles governing existence. At the level of quantum fields, empty space is not truly empty. Virtual particles continuously emerge and vanish. Fluctuations generate energy, and the vacuum itself possesses a form of density. When physicists calculate the energy associated with this vacuum, the numbers are staggering. The predicted density is many orders of magnitude greater than what cosmological observations indicate. Gravity should be dominated by this energy, driving expansion at rates that would prevent galaxies, stars, and planets from forming. Yet here you are, in a universe that expanded slowly enough to allow structure, life, and observation. The prediction and the reality diverge dramatically, but the universe persists, accommodating the discrepancy without explanation. This mismatch, the cosmological constant problem, is one of the most unsettling in physics, precisely because it highlights a fundamental gap between calculation and observation. Quantum mechanics and general relativity, individually precise and experimentally confirmed, suggest vastly different outcomes when combined. The vacuum energy that seems mathematically unavoidable does not manifest as expected in the dynamics of space-time. The universe tolerates the mismatch without collapse, a silent reconciliation that is not understood and may point to physics beyond current theory. The implications extend to the notion of naturalness. Physical laws are generally assumed to produce values that are typical or consistent across scales. The cosmological constant violates this expectation. Its observed value is extraordinarily small compared to quantum predictions. Yet it is not zero. The universe operates with a delicate balance, sufficient vacuum energy to drive acceleration, yet small enough to allow galaxies to form and observers to exist. This precise tuning is measured, not predicted, and the mechanism enforcing it is entirely unknown. You inhabit a cosmos that functions smoothly despite an internal energy mismatch that is mathematically catastrophic by conventional reasoning. Observationally, the evidence is clear. Type Ia supernovae, the cosmic microwave background, and baryon acoustic oscillations all indicate a slowly accelerating expansion. Gravity acts on scales of galaxies and clusters as if a small, uniform energy permeates space. Yet this empirical measurement is dwarfed by theoretical predictions by a factor of at least 10 to the 60. The numbers are not close. They are inconceivably distant. Every calculation that predicts a large vacuum energy seems to ignore the reality you can measure. Every observation that confirms a small cosmological constant implies that some unknown mechanism suppresses the vacuum's effect on cosmic expansion. This discrepancy challenges assumptions about measurement, theory, and the coherence of physical law. You assume that theoretical frameworks, once tested and validated in one domain, extrapolate reliably to others. Yet the cosmological constant problem demonstrates a domain in which extrapolation fails spectacularly. Reality accommodates a parameter whose magnitude is far outside expectations, without violating observed laws or preventing the emergence of complexity. Your understanding of energy, gravity, and space-time is therefore provisional, conditioned on a discrepancy that lacks explanation. The problem also carries philosophical weight. It suggests that the universe's behavior is not entirely constrained by mechanisms you can calculate or anticipate. Fundamental constants, the dynamics of vacuum energy, and the large-scale expansion may be governed by principles that remain hidden. You perceive order, but underlying it is tolerance for vast numerical mismatch, a hidden hierarchy of influence that shapes existence without disclosing its method. The universe functions, persists, and evolves in a way that is mathematically counterintuitive, yet empirically undeniable. The cosmological constant problem is a reminder that the universe is stranger than theory alone predicts. calculations suggest a catastrophe. Observations reveal stability. The universe carries immense, invisible energy, yet balances it with precision no one fully understands. Every measurement you make, every model you trust, exists atop a foundation that tolerates contradictions on a scale that defies comprehension. Nature reconciles extremes you cannot perceive, and in doing so, exposes the provisional limits of knowledge. Parallel realities in quantum measurement. Every measurement collapses probabilities into a single outcome. Yet interpretations, like many worlds, suggest that every possibility branches into separate realities. Your choice, your observation, creates divergence, hinting that your experience may be one of countless overlapping realities, each as real as the one you inhabit. When you interact with the world, you assume a single, coherent history. You flip a switch, observe a particle, or decide a course of action, and the universe seems to yield a singular, definite result. Classical intuition presumes that one outcome manifests and all alternatives vanish. Yet quantum mechanics suggests otherwise. Particles exist in superpositions, multiple states simultaneously, until an interaction produces a measurable effect. Each measurement selects an outcome, but interpretations, like the many worlds hypothesis, argue that selection does not erase alternatives. Every possibility continues in a separate, non-communicating branch of reality. This branching is not theoretical speculation in the ordinary sense. It is a logical consequence of the formalism of quantum mechanics. Schrödinger's equation evolves the wave function deterministically. Superpositions are real. They evolve according to precise rules. When observation occurs, decoherence separates branches of the wave function into effectively independent realities. In this framework, the universe constantly bifurcates, producing a staggering multiplicity of histories that are as real as your own. The world you perceive is only one branch among uncountable others. The implications are profound. Every decision, every measurement, every interaction potentially generates new realities. You may choose a path in one branch, while an alternate version of yourself chooses differently in another. Galaxies collapse in one history, expand in another. Particles decay in one branch while remaining stable in another. Continuity, causality, and outcome are contingent upon the branch you inhabit. The determinism of the wave function is absolute, yet the unfolding of experience appears selective, local, and singular. Reality is simultaneously singular and infinitely manifold. Observation itself acquires new significance. Your act of measurement is not passive. It participates in the proliferation of realities. Every observation you make, The flicker of a photon on a detector, the reading of a clock, the judgment of an event, defines a path through a branching multiverse. Your consciousness and the world you experience corresponds to one coherent branch, but countless others unfold in parallel, inaccessible yet equally real. The singularity of your experience is provisional, defined by the branch you inhabit. This framework also challenges assumptions about probability and expectation. What appears statistically improbable in your observed reality may be common in the multiverse as a whole. Low probability outcomes manifest in some branches, high probability outcomes in others. Your perception of randomness is therefore a local phenomenon, an artifact of inhabiting one branch among infinitely many. The universe contains every allowed outcome, yet your perception samples only a fraction of the total ensemble. Even physical laws are subtly implicated. Each branch respects the same fundamental rules, yet their cumulative histories diverge wildly. Stars may form in one reality, while failing to coalesce in another. Life may emerge in some branches, and not in others. The cosmos you observe is one coherent narrative extracted from a web of overlapping, non-communicating realities, each obeying the same physics, but producing distinct histories. Your sense of singular existence is therefore provisional. You are one observer, one sequence of events within an immense superstructure of realities that unfold in parallel. Every measurement, every decision, every interaction generates divergence, producing layers of existence that are inaccessible yet implied by the formalism of quantum mechanics. The world you inhabit is not unique. It is one path through a branching, infinitely complex multiverse. Continuity, identity, and outcome are local properties, emergent from the vast proliferation of parallel realities that exist as a fundamental consequence of measurement. The singularities, hidden laws. You assume the laws of physics apply everywhere. At a singularity, density becomes infinite, curvature diverges, and time as a concept breaks down. The mathematical models indicate that our understanding ceases, not because phenomena are inaccessible, but because reality itself violates the framework we rely upon. In classical general relativity, a singularity is a point where the equations describing space-time produce infinite values. Mass is compressed into zero volume. Gravity becomes unbounded, and the curvature of space-time grows without limit. These are not abstract curiosities. They are predictions derived from equations that have been verified in ordinary conditions. Yet, at the singularity itself, the formalism collapses. Concepts you take for granted, distance, time, causality, lose meaning. The rules that govern planets, light, and galaxies no longer operate. Your assumptions about reality, grounded in empirical law, encounter a boundary where mathematics itself signals its inadequacy. The breakdown is not merely practical, it is fundamental. Singularities are not hidden behind ignorance or incomplete observation. They are, according to theory, locations where the structure of space-time and the dynamics of matter produce infinities, indicating that the very framework of physics fails. No measurement could reconcile the divergence because the concepts of measurement, duration, and spatial separation lose applicability. The universe, in these conditions, does not merely defy prediction. It defies the applicability of law. The singularity is not inaccessible. It is an environment in which law has no operational meaning. Black holes provide the most tangible encounter with this phenomenon. As matter collapses beyond the event horizon, gravitational forces compress it toward a central singularity. All trajectories converge, all distinctions are eliminated, and the core region becomes a realm where space-time curvature diverges. From the outside, the black hole is well described by mass, charge, and spin. Internally, the singularity remains a domain in which the equations you rely on fail completely. Reality itself presents a region that cannot be described, not due to lack of data, but due to the inapplicability of existing frameworks. This failure has deep implications for the concept of universality in physics. You may assume that the same laws govern every corner of the cosmos, yet the singularity challenges this assumption. It represents a condition in which continuity, predictability, and determinacy collapse. The physics that allows you to understand light bending, planetary orbits, and quantum interactions simply does not extend to this domain. The universe contains regions where law, as we understand it, is not just incomplete, it is structurally absent. The singularity also undermines the notions of causality and time. Time, measured by the ticking of a clock or the sequence of events, ceases to function as a coherent parameter. Past, present, and future collapse into an undefined point. Any process, any sequence of events, loses context. The universe permits existence of locations where chronology itself has no meaning, where the causal relations you rely upon cannot be defined. These are not theoretical artifacts. They are intrinsic to the mathematical description of extreme gravitational collapse. Even attempts to reconcile singularities with quantum mechanics through hypotheses of quantum gravity or string theory highlight the unknown. The singularity is not merely a limit to knowledge. It is a limit of reality itself as it intersects with our mathematical and conceptual frameworks. Matter, energy, and space-time exist in ways that cannot be represented, predicted, or measured using the principles that govern the observable universe. The singularity is simultaneously real and unknowable, a point at which the universe refuses description. Your perception of continuity, determinism, and law is therefore provisional. Singularities reveal that reality contains domains in which the familiar structure of existence does not apply. The universe you inhabit, with predictable forces and observable regularities, is contingent upon remaining far from these extremes. At the singularity, your assumptions collapse. Space, time, and causality dissolve. The hidden laws of the singularity suggest that the cosmos harbors regions that are fundamentally, irreducibly, and permanently beyond comprehension, where reality itself operates in ways that cannot be reconciled with experience or measurement. Gravitational waves as cosmic messengers. You perceive space as static, but massive objects in motion produce ripples in space-time. Gravitational waves travel vast distances, carrying information about events you could never see. The universe communicates in silent vibrations, detectable only through sensitive instruments, reminding you that perception is limited to what interacts with matter and light. Every massive object in motion affects space-time. Planets orbit stars, stars orbit galactic centers, and massive binaries spiral toward each other. These motions are continuous, predictable, and largely imperceptible in terms of space-time distortion. Yet when objects of extreme mass accelerate, colliding black holes, merging neutron stars, they generate waves that propagate outward at the speed of light, stretching and compressing space-time itself. The fabric of the universe vibrates, carrying information about events that are otherwise inaccessible. Detection of these waves is not straightforward. Their effect on matter is minuscule. Earth-based interferometers measure changes in length smaller than a fraction of a proton's diameter over kilometers of distance. Yet these tiny distortions reveal the most extreme cosmic events. A binary black hole merger, billions of light years away, produces a signal that propagates unimpeded through the void, unaffected by intervening matter. What you perceive as empty space is therefore a conduit for information, silently transmitting the history of the universe across incomprehensible distances. Gravitational waves also expand the domain of observation. Light, electromagnetic radiation, and particles interact with matter, often limiting what you can detect. A supernova in a distant galaxy may be obscured by dust or its light too faint to register. Gravitational waves, however, are indifferent to opacity, passing through regions that block all other forms of communication. They encode the dynamics of mass, rotation, and acceleration in a pure form, independent of intervening material. Your perception, reliant on photons and charged particles, captures only a fraction of what is occurring. The universe conveys its events in ways that are fundamentally imperceptible to ordinary senses. These waves are also messengers of extreme physics. A neutron-star collision encodes information about matter at nuclear densities. A black hole merger records the space-time geometry under conditions of maximal gravity. The signals you detect are direct reflections of phenomena that cannot otherwise be reconstructed. Reality preserves a record of the extreme, imperceptible, and remote, transmitting it through ripples that are simultaneously subtle and all-encompassing. The universe operates as a vast archive, and the waves are the medium by which it communicates across the void. Gravitational waves highlight the limitation of intuitive perception. You may assume that observation is tied to visibility, that events are relevant only when they emit light or interact with matter. Yet the universe functions independently of this assumption. Massive motions, violent collisions, and distortions of space-time occur whether or not they are observed in the conventional sense. Detection requires extraordinary instruments, precise calibration, and careful analysis. Yet the underlying events are indifferent to your presence. Reality is persistent and communicative in ways that exceed intuition. The waves also imply an underlying coherence in the cosmos. Every ripple, every vibration is shaped by universal laws, propagating deterministically through space-time. Yet the information they carry can be subtle, complex, and counterintuitive. Interpreting a waveform reveals the mass, spin, and dynamics of distant objects, translating the silent language of geometry into measurable data. You are confronted with the fact that the universe conveys information through means that are invisible, non-material, and non-photonic, demonstrating that perception is always partial and contingent. Every moment, space is vibrating, shaped by motions and interactions far beyond your local frame. The silence you experience is an artifact of sensory limitation. The cosmos is alive with oscillations, subtle, persistent, and universal, recording events beyond light, beyond matter, and beyond ordinary observation. Gravitational waves are the universe's quiet testimony, carrying the echoes of cataclysm and motion across the void. They reveal a reality in which existence, motion, and consequence persist independently of perception. And your experience captures only a fraction of the information encoded in space-time. The limits of observability. Your view of the cosmos is finite. Light from beyond a certain distance has not yet reached you, and some regions are forever beyond causal contact. Observation is bounded by horizons, and reality extends indefinitely into regions your instruments cannot access. You live inside a bubble of perception, unaware of what exists beyond. Every observation you make is constrained by the finite speed of light. The photons that arrive carry information from the past, from a universe that may have changed dramatically since their emission. You see stars and galaxies as they were millions or even billions of years ago, not as they exist now. The present, the here and now of distant objects, is forever inaccessible. You perceive a universe that is inevitably incomplete, a mosaic constructed from fragments of information that have traversed vast distances over enormous spans of time. Beyond the observable limit, known as the cosmic light horizon, the universe continues. Regions beyond this boundary may mirror what you see, or they may be radically different. You cannot measure, detect, or interact with them. They exist, but their properties are causally disconnected from your location. Expansion of space ensures that some regions will never enter your light cone, no matter how long you wait. The universe, in this sense, is larger than any possibility of observation, carrying structures, events, and histories that will remain permanently inaccessible. Even within your observable bubble, observation is mediated by attenuation, interference, and bias. Light can be absorbed, scattered, or redshifted by intervening matter. Gravitational lensing distorts distant images. What you perceive is a filtered, processed subset of reality, shaped by the conditions of transmission, rather than the intrinsic nature of distant objects. Your instruments extend perception, but they cannot overcome the fundamental limits imposed by causality and distance. Observation is necessarily partial, contingent, and provisional. This limitation has consequences for your understanding of cosmology. You can infer large-scale structures, measure the expansion of the universe, and detect the cosmic microwave background. Yet all inferences are constrained by what can reach you. Beyond the horizon lies a realm that is unknowable in principle. The universe contains domains in which matter, energy, and dynamics may differ, yet you cannot incorporate them into models, measure them, or confirm their properties. Reality extends indefinitely beyond the finite sphere you inhabit. The horizon also affects your conception of time. Light carries the record of the past, and you observe regions as they existed long ago. The present of distant domains is inaccessible, leaving a temporal gap that grows with distance. Your experience of simultaneity is local, and universal simultaneity is ill-defined. Events occurring in distant, unreachable regions unfold independently of your perception, yet contribute to a cosmos whose full extent you cannot measure or know. Cosmic expansion compounds the limit. Space itself stretches faster than light in some regions, pushing them irreversibly beyond contact. Galaxies that exist today within your causal future may never become observable. You live in a universe in which expansion, distance, and light speed constraints produce permanent isolation, no matter how advanced measurement becomes. Some parts of reality are intrinsically hidden, forever outside the scope of observation. The limits of observability reveal the provisional nature of all cosmic knowledge. Your maps, models, and theories describe only a fraction of existence. What you see is embedded within a boundary defined by causality, light, and expansion. Beyond that boundary, the universe continues, vast and uncharted. You inhabit a bubble of perception, finite and constrained, within a reality whose totality exceeds measurement, experience, and comprehension. The cosmos is simultaneously accessible and inaccessible, knowable and permanently hidden. Every observation is a partial glimpse, every measurement a local truth, and every model a projection onto the finite portion of reality that touches your light cone. Your experience of the universe is thus defined by limits of light, of causality, and of horizon. Beyond your perception, existence continues, indifferent to observation, unmeasured and unreachable. The universe stretches outward, extending indefinitely into the unknown, leaving your understanding provisional and fragmentary. A bounded window into a cosmos far larger, older, and more complex than you can ever perceive. Vacuum metastability. You assume the vacuum is stable. Quantum calculations suggest it might be metastable, prone to decay into a lower energy state. Such a transition would propagate at light speed, altering fundamental constants and annihilating structures. The universe as you know it may persist only because it has not yet crossed an invisible threshold. Empty space is not empty. The quantum vacuum seethes with fluctuating fields, virtual particles, and ephemeral energies. These fluctuations define the energy landscape of the universe, shaping the behavior of matter, radiation, and forces. In a metastable vacuum, the energy you perceive as normal is not the absolute minimum. A lower energy state exists, separated from your current state by a barrier that quantum processes can, in principle, overcome. The universe is poised, delicately balanced on the edge of a more stable configuration. Such a decay is not gradual. If a region of space transitions to the lower energy vacuum, a bubble of true vacuum forms. Its boundary propagates at nearly the speed of light. Within this bubble, the laws of physics, the values of fundamental constants, and the properties of matter would be radically different. Atom could not form as they do. Chemical bonds would break, and structures built over billions of years, including planets, stars, and life itself, would be destroyed instantly relative to the propagation of the bubble. Your perception of continuity would be irrelevant. The change would occur faster than any signal could warn of it. Quantum mechanics implies that such decay is possible, even if exceedingly unlikely. The lifetime of the current vacuum state may exceed the age of the universe by many orders of magnitude, but the mere possibility is unsettling. What seems permanent and stable, the uniformity of space, the constancy of physical laws, is contingent upon a landscape defined by probability. The universe you experience is a realization of one local minimum in an energy field that could contain lower, inaccessible minima hidden beyond quantum thresholds. Observation cannot detect impending decay. No measurement, no instrument, no astronomical survey can reveal whether the vacuum is absolutely stable or metastable. The existence of a lower energy state is inferred from particle physics and high-energy calculations, particularly regarding the Higgs field. Its mass and coupling parameters suggest that your vacuum may lie precariously on a slope rather than a deep valley. Stability is provisional, contingent upon precise values that are measured yet unexplained in origin. The universe operates in a regime that is mathematically consistent but potentially impermanent. This possibility challenges assumptions about permanence and causality. You perceive matter, time, and space as continuous and enduring. Yet vacuum metastability implies that continuity is contingent, that the rules and constants you rely on are provisional, and that reality can undergo irreversible transformation without warning. The universe does not signal impending collapse. Its stability is an artifact of probability and circumstance, a temporary persistence within a broader landscape of possibilities. Furthermore, the concept underscores the fragility of the physical world. Life, galaxies, and even the existence of you as an observer are built upon constants that may not be absolute. Quantum mechanics allows that the current arrangement could spontaneously give way to a different regime. Every measurement, every physical law you observe may be contingent upon a vacuum configuration that could, in principle, cease to exist in its current form. The apparent permanence of the cosmos is, therefore, provisional, an emergent feature of an underlying quantum uncertainty. The universe's survival is not guaranteed, only probabilistic. You inhabit a cosmos that is stable only because it has not yet crossed a threshold you cannot perceive, a transition you cannot detect until it has occurred. Reality persists in the present configuration as a product of improbably long lifetimes, not absolute permanence. Every moment, space teeters on the edge of a potential state change, and your experience of continuity and law is maintained only because quantum fluctuations have not yet breached the barrier. Vacuum metastability reminds you that the apparent stability of existence is conditional. The cosmos endures, but its endurance is provisional. Beneath the familiar constants, matter and time, lies a landscape of hidden energy, probabilistic and indifferent. The universe continues only because decay has not yet occurred, and the fragility of this persistence is invisible, unobservable, and absolute. The reality you inhabit may be a temporary island within an energy landscape far vaster, deeper, and more uncertain than perception allows. Entropy and the fragility of existence. You perceive order as persistent. Structures endure, life persists, information survives. Yet entropy dictates that all organized systems tend toward disorder. Your existence, your surroundings, and every record of history are temporary arrangements in a universe trending inexorably toward decay. Stability is a fleeting, fragile phenomenon. Every system you encounter, your body, the Earth, the planets, and even galaxies, maintains its form only because energy flows through it in specific patterns. At local scales, order emerges from the transfer of heat, the movement of matter, and the interaction of forces. These arrangements, however, are not permanent. They require constant energy input to resist the natural tendency toward equilibrium. Without continuous replenishment, structures degrade, molecules break down, stars burn out, and galaxies gradually disperse. What you perceive as permanence is a temporary suspension of decay, maintained against the universal current of entropy. Entropy is not an abstract concept. It is a measurable property, quantified in terms of energy dispersal and the number of accessible microscopic states. Every organized structure, from a protein in a cell to the orbit of a planet, occupies a highly ordered configuration relative to the countless disordered possibilities. The universe, taken as a whole, evolves toward states of higher probability, states with greater disorder. Your experience of stability and continuity is thus improbable, contingent, and ultimately transient. Time is inseparable from this process. The arrow of time, the apparent unidirectional flow from past to future, is a consequence of increasing entropy. You perceive cause and effect, memory and history, because entropy progresses. Yet this progression ensures that every structure you rely on, every record you maintain, and every phenomenon that appears stable is gradually eroding, moving inexorably toward dissolution. What seems fixed and enduring is, in fact, ephemeral. The universe enforces impermanence at every scale. Even information is subject to this fragility. Written records, digital files, and the molecules encoding memories all decay over time. The arrangement of matter that constitutes knowledge is provisional, sustained only by energy inputs that counteract diffusion and thermal motion. Without intervention, the universe erases every mark of history. Entropy ensures that permanence is illusory. Survival of form and function is temporary, a local and fleeting defiance of universal decay. Entropy also governs cosmic structures. Stars burn nuclear fuel and collapse. Galaxies interact and merge. Black holes gradually absorb mass, and radiation disperses energy across space. The cosmos you observe is not static. It is a dynamic system in which order is continuously generated, sustained, and ultimately consumed. Your perception of continuity is nested within a vast temporal process that guarantees the eventual breakdown of every structure you can detect. The fragility of existence is compounded by the scale of the universe. On Earth, life survives by harnessing energy from the sun, maintaining localized low entropy at the expense of increasing entropy in its surroundings. Galaxies form and persist for billions of years, yet their coherence depends on delicate gravitational balances. Even the universe itself trends toward a high entropy state. As expansion continues, energy becomes more diffuse, stars exhaust fuel, and the cosmos approaches a uniform, cold equilibrium. What you experience as vibrant and structured is but a temporary phase in a long-term trajectory toward uniformity. Entropy reveals the provisional nature of all that you consider real. The order surrounding you is contingent, temporary, and constantly under threat from the universal tendency toward disorder. Every structure, every form of information, and every living being exists within a fleeting window of improbability, maintained against the relentless drive toward equilibrium. Stability is not guaranteed. It is a local, temporary defiance of a fundamental principle that governs all reality. Your surroundings, your life, and every record of history exist only because entropy has not yet fully asserted its influence. The universe sustains order as a temporary, fragile arrangement. All that seems persistent is contingent upon the constant battle against decay. Every moment you perceive continuity, every structure you rely on, is impermanent. The cosmos is not forgiving, and the fragility of existence is a fundamental property of reality, a quiet reminder that stability is a fleeting anomaly in a universe ruled by entropy.